All right. So our next speaker here is a lead security operations center architect at Block Harbor Cybersecurity. Mike lives to crush the deliberate denial of the emergency that is the cyber to physical security landscape. Just because it's not easy doesn't mean that we can't put our doesn't mean we can put our hands over our eyes, slip on our headphones, and ignore what's happening. So Mike speaks, writes, and works in the field to help people recognize and promote positive solutions that are so desperately needed. Mike works in the automotive and financial cybersecurity fields. Yes, he is a truly multifaceted cyber warrior. He currently serves as the lead security operations center architect for Block Harbor Cybersecurity out of Detroit, Michigan, and is the chief information officer of a financial analytics startup, RapidCat, based out of Raleigh, North Carolina. After realizing glaring vulnerabilities in financial technologies and e-commerce systems early in his career, he's since pivoted to securing systems to include software, web applications, and now his research is in the cyber-physical technology arena. He's a passionate researcher in exploring the increased attack surface that connected cyber-physical devices present in our everyday lives, exploring what can go wrong and how to secure IoT, ICS, IOTM mobility infrastructure that humankind relies on to push towards increased technological advances and keep people safe every day. Since cementing his expertise in this arena, he's taken to the public stage, presenting his insights and finding through a number of talks, conferences, and panels, and we are really happy to have him here. BSides RDU is also presenting him with a speaker gift, a sneaky book. So welcome to the stage, Mike Curnow.
Thank you for that very short intro. It was, yes, the moment that we've all came here for. So why we're at BSides 2019 right now. The intermediate guide to navigating Active Directory. No, I'm kidding. But the rest of the presentation is going to be that much more interesting, so set the bar low. Yeah. Anywho's, but yeah, so welcome to Let's Get Cyberphysical. Learn it. See it. Secure it. By yours truly. Wait for it. Okay, that's me. I have 60 minutes to cover a lot of shit, so I'm going to be speaking pretty quickly at some points. So I'm going to just get that out there beforehand. So who am I? A little bit about me personally. I'm always tripping or falling. Me at my baby shower, I tripped, someone caught on camera. I don't really get art. I like fidget spinners. That was staged. That wasn't candid, by the way. And I have a hard time being comfortable while wearing a suit. Belong to a very distinct group of people. So, the professional side, got my start in financial technology. Worked as a software integration engineer. For a financial tech company, and basically I was writing code to do things that would now be used for MageCart, which is the injection of front-side code that scrapes payment information, sends it to a place. I wrote it in a way that sent it to a financing platform that would, run your eligibility and fraud checks through different lenders, that kind of thing. I was the head of security services for an international MSP, formerly a programming cybersecurity instructor for the Coder School. Did that for about 3 years. Currently, the lead security operations center architect for Block Harbor Cybersecurity, which is a cybersecurity firm based out of Detroit, Michigan, that specializes in cyber-physical security. So securing things that start with a digital instantiation, then have a physical effect in the real world. And we have a foothold in mainly automotive, so working with automotive OEMs to secure the cyber-physical systems that they use in the manufacturing side and or the dealership side, so like when you go get your car fixed. They use devices that plug into the vehicles and they connect to the cloud and all that kind of cool stuff. Co-founder and chief information officer for RapidCat. RapidCat's a financial analytics startup that basically tries to, we use machine analytics and pretty complex stuff to try and help lower the barrier of entry for people trying to get into the Forex binary market. Trying to make it easier for so everyone can do it. You wouldn't think it, but I do a lot of public speaking. This is my 4th out of 5 conferences this year. Do different panels, meetup talks. Just got done doing a 2-day, 6-hour cybersecurity seminar, which had my throat dead. So a little bit about my experience. The compulsory red team side, I got my start in doing penetration testing, and been a senior pen tester. Doing vulnerability assessments, social engineering campaigns on different organizations. Now I've done defensive security, blue team side. A lot of what I've done is mainly in the development and architecture of security operations centers. So basically all the plumbing and whatnot that goes into gathering and aggregating data from multiple sources, centralizing all that, doing the analysis and doing all the correlation, setting up the alerts, and then setting up also the policies that people follow in a SOC. Then industrial control systems. Got my start doing a SCADA pen test on a major piece of metropolitan public transportation. That was my first exposure to it, and after completing that test, I ended up falling in love with industrial control systems. Then on the research side, I spent a lot of my free time really specializing in the ICS and OT convergence. So basically, converging physical systems to talk to cloud systems in a secure manner, and working in IoT. So there's doing stuff with MQTT brokers on the IoT side, just a device-to-device protocol that lets devices talk to each other in the IoT realm. Automated tank gauges, did a lot of work with identifying tank gauges that are out there. These tank gauges are open to the internet for gas stations so that they can hook up their gas stations to different management platforms. Another part of the IT-OT integration. Then a lot of IOMT, but mainly in insulin pumps. So basically automated insulin pumps that you have either a phone or a management handheld device that allows you to manage the operation of an insulin pump that sticks into your arm. Really good stuff, really convenient, helps a lot of people out. A lot of RF type hacking, mainly just a lot of capturing signals, replaying them, seeing what works, what doesn't, trying to break some decryption on captured signals. Then my latest and greatest thing that I've been spending a lot of time in is identity-defined oriented network, which is basically adding a new layer, a new namespace to the network conversation. So you've got IP address, you've got DNS, and then you have the actual host identity, which is a cryptographic identity that's used to solidify the identity of the device you're talking to, so you're not getting spoofed. So what I'm going to be talking about today, cyber-physical technology, what it is, why it's important, or what role it plays in our lives today. The problem, which is security. Security is the problem, or lack thereof, you dig? Facets of cyber-physical security. So basically, going over the different realms of cyber-physical security. And then we're going to be looking at Internet of Medical Things. We're going to be looking at automotive, like connected cars. We're going to be looking at industrial control systems. It wouldn't be a Mike Curnow talk if I didn't beat the dead horse on ICS and then beat the dead horse of its next of kin. multiple times. Then we're going to do attack scenarios, and it's a combination between some demos and movies I have, doing IOMT, automotive, ICS, and then we're going to talk about some perspective ways or ideas or mindsets or notional concepts, whatever abstract term you want to assign to it, ways to secure these. So these are just to kind of get you in that mind space. And there might be a surprise parting gift later if it works. Anyways, yeah, so to kind of dig right in, or get right into it, cyber-physical systems are systems that are comprised of interacting digital, analog, physical, and human components engineered for functioning through integrated physics and logic. Basically, it's just you have an electronic thing that happens on a computer somewhere that then turns into a reaction in the real world. So like factory equipment or something, right? It's the easiest way to think about it. Cyber-physical security is protecting the assets on a network from a cyber attack wherever physical harm can be caused. Physical harm, damage to property, loss of life, these are all things that, you know, we want to prevent, I think, right? The importance of cyber-physical systems, they are pretty much embedded in our society, and they're going to keep getting embedded in our society. So I have this definition from CPSC Labs here. CPS, or cyber-physical systems, are identified as a core enabling disruptive technology that allows us to continue all the stuff in embedded systems, and it basically helps us tackle a bunch of issues. And I'm not going to read the whole thing, but I'm sure you can read that. But so to kind of get a better grasp on cyber-physical technology and the importance of it and why I'm talking about it, we need to talk a little bit about the industrial revolutions that happened before now. Right now, we're in Industry 4.0, which is basically the computerization and the interconnectivity of everything. But we need to do a little history lesson on what happened before. So I'm going to try and go through these relatively briefly here. So you have Industry 1.0, the mid to late 1700s. That's when we kind of pivot our economic structure from agriculture to industry. We have steam engine, coal mass extraction technologies introduced, and then the acceleration of economic, material, and human-driven exchanges. So we have locomotives and railroads for goods and people transportation. And then that inherently created a foundational blueprints for industrial factories today. Industry 2.0, that takes place in the late 1870s, and we have new energy introduced like gas, oil, electric, combustion engines created that also subsequently creates a need for steel. So the steel industry grew exponentially. New communications like telegraph, telephone, along with transportations like automobile and the airplane. Industry 3.0 takes place in, starts 1969-ish. We have new energy, which is nuclear. We have new electronics, so we have the transistor, microprocessor, all that stuff listed here. Miniaturized materials, space research, biotech. Then revitalizing the industry through automation, right? So that's robots and things that constitute industrial control systems. And Industry 4.0 now is a little bit bigger. We have the 9 pillars of Industry 4.0. So we have virtual, augmented reality, additive manufacturing, building from the bottom up instead of taking raw material and chiseling away at it until it becomes what you want it to be. Internet of Things, which is everywhere. Big data, cloud computing, advanced simulation, autonomous robots to think, act, and react. Universal integration, just basically the interconnectivity from systems to systems, which is a huge part, and then cybersecurity. So cyber-physical exists in the majority of these different pillars in different ways. So without cyber-physical systems, our Industry 4.0 advance isn't really going to happen. And we need cybersecurity to secure those pillars and to secure the universal integration. So cyber-physical systems are everywhere. That's what this graphic is denoting. So the problem, which is security, or the lack thereof, I'm going to get into a video here, just kind of identifying the process of provisioning a cyber-physical service, the use of it, and then how it can go wrong. This might be a little bit loud at first, so I'm going to try and temper that down a bit. If anybody is familiar with the show Black Mirror, I think you're going to recognize this episode. If not, that's fine too. But just a piece of context there. Keep my hand on the volume just in case. That's the problem. Bees went extinct. The solution, which is fake robot bees to supplement. And the problem with this.
You said you get some malfunction. 30 years, they smack into a car. We had to track them. Put them in the microwave for YouTube. And this logs any that drops the system. Logs everything. Who's any around here? This one. 90 hours. Here I replay. A hole dug in, a borehole, it's like a tunnel. So I follow it, you know, how deep does it go? It goes all the way from that ear canal to
It's a dead body.
our brain. What I find is this nestled right in there. Looks quite cozy.
Whoa, no way.
No, they are. I say it's probably. That's not the worst part. Crawled right through the dorsal posterior insula.
That's how they work. And then the aftermath, or the dumpster fire. Notional dumpster fire.
But that's not. Stop, stop. Say that again? It's very close.
We don't want to be saying this, all right? We don't ever want to get into a situation where we find we have a problem, we find a solution really quick, we throw it out there because it's feature rich and people will love it and it'll make lots of money without securing it first, right? So this is, again, from Black Mirror. It's a little bit of hyperbole in here, but the idea is still the same. These cyber-physical solutions can be put out into the ether without proper security, right? So it's basically kind of like a drawn-out, crowdsourced QA problem. So the facets of cyber-physical technology, there's a lot of them, so I just kind of put what I could on this slide here. But if you were to imagine that this sphere represents cyber-physical security, then also this spinning dodecahedron is a representative of the multifacetedness, which is a word, I think, of cyber-physical. And the cool thing about a dodecahedron is that you can always be friends with it because it's a platonic solid. Yeah, I knew it was pretty good, right? Okay, so to kind of draw upon this a little bit, or dig into this a little bit more, you have this diagram right here that kind of illustrates the taxonomy of the cyberphysical systems. And we can see cyberphysical systems are feedback systems that have humans, economics in the loop. They require cybersecurity, improved design tools, and design methodology. And they have applications in all of these right here, and then some. And this diagram came out of a project that somebody was doing through the NIST project, or for NIST, and then coming up with that. So, get a little bit more into this. We have smart grid. Just smart grids are pretty much just an electrical supply network that uses digital communication tech and smart meters and appliances to detect and react to local changes in usage. And we have robotic systems that use sensors, actuators, and human interface to provide intelligent service and information by interacting with their environments. Then industrial control systems, collective term using to describe the different types of control systems and everything associated with that, including all the instrumentation. So the devices, the systems, the networks, and controls that are used to automate industrial processes, manufacturing plants, light, electrical, water treatment facilities, that kind of thing. Automatic pilot avionics. So automatic flight control systems, they're just the systems that control key operations of the plane in its flight. So they also handle electronics and stuff, things for like communication, navigation, collision avoidance, and weather. And the original use was just to provide a pilot relief during tedious stages of flight, such as high altitude cruising. But advanced autopilots can do much more, carrying out more precise maneuvers. And we have photovoltaic systems. These are basically just solar power systems, right? So it's a power system designed to use solar power as a means of energy. And so I actually found something in the wild that was pretty interesting. There was a school in New England that's kind of well known that purchased a plot of land a few years ago. There used to be a reform school or a boarding school or something, and they bought it. They bought this land. They're like, hey, fuck it, we're just going to put solar panels everywhere. And their control system was open to the internet. And so I found it. I found there's it was the technology that was well known in that space, so that you can just find the default logins and get in there. But also, it runs over Modbus, so you can do pretty simple queries to the Modbus controller. Turn it off if you wanted to, really, which is pretty dangerous. But we let them know. We let them know this, and we gave them pretty much all of our research and said, hey, please fix this. Half of it's fixed. Can't get into the control panel, but you can still talk to the controller. So essentially, it's not fixed. Connected vehicles. Vehicles are now equipped with internet access and Bluetooth and other ways of doing fancy communication stuff. Connected cars, the hope for the future is basically that cars can talk to each other and trade important safety and mobility information in transit. Then next we have the Internet of Medical Things, or IoMT, which is basically it's IoT, but specifically for healthcare devices. So things like blood pressure monitors, X-ray things, pacemakers, the insulin pumps. Smart homes, which if you can find a lot of these on Shodan. There's a lot of them in upper New York State. I didn't tell you that, but I just happen to know a guy. Yeah, so much other shit. It's everywhere and in everything, and will be in everything. So smart toilets, right? Kohler has they're selling a toilet now that has Alexa built in. Yeah, so imagine, yeah, imagine like your significant other, in my case, my wife leaves the house really quickly and leaves her keys inside and is knocking at the door. While defecating, I can lean over and say, "Hey, Alexa, unlock the door," because the Alexa from my toilet will be connected to the smart home system in my home, controlling the temperature and the door locks and everything. So we are entering the age of Wall-E. That's just one man's opinion. And again, I tend to be a bit hyperbolic with some of these, but it's just really me trying to drive a point home, you know? So the three facets we're going to be concentrating on today are Internet of Medical Things, automotive, and industrial control systems. So some of you have been to my talks before or sat in on other presentations, so some of the ICS stuff will be a little bit familiar to you, but I added some extra spicy things at the end, so I think it'll be really interesting for you all. So yeah, without further ado, let us begin. See what I did there? So yeah, Internet of Medical Things. We talked a little bit about that, but basically what the Internet of Medical Things is a way of IoT expanding into the healthcare space, right? And so we have a pacemaker that connects to an app on your phone. Pretty cool. The idea of it's pretty cool, right? But the security implications are very wide. Now, this particular application, I did do some research on it, and it says that only ingests data coming from the pacemaker, but I need to get my hands on one of these. And then next, I've done a lot of research in the insulin pump arena. So really, the things about the IoT is, or IOMT is, they lower costs. So like using IoT solutions and connected medical devices allows healthcare providers to monitor patients in real time, meaning like less unnecessary visits to the doctor, less hospital stays and readmissions. There's a better patient experience because being connected to the healthcare system through the Internet of Things, patients get more engaged in their treatment. They're actually more of a part of it, and the doctors can improve diagnosis accuracy since they have all the necessary data on hand already before the patient even comes in. Better management of drugs and medicine adherence. So, basically allowing staff to spend less time searching for drugs, tracking supplies and medicine, and all the logistical aspects, and track hygiene practices in hospitals, make sure that they're effectively preventing hospital infections. They also help patients adhere to the treatment plans and the doctors to kind of, maintain that integrity for them, making sure they're staying on track with their medicinal regimen. Reduced errors and waste. So using IoT for data collection and workflow automation is a good way to cut down on the waste. Reduce system costs and minimizing errors, especially ones that can be due to the human factor, right? Human error. And improved outcomes of patient treatment. So healthcare solutions that are connected through cloud computing and using the big data can provide caregivers with the ability to access the real-time data they need to better take care of their patients. So here's a video. Here's a video that I did. This is, I have a insulin pump, and I do some, I'll talk through as I'm going through it. So basically here we have a Omnipod PDM. We have an insulin pump that you can put insulin into. It works better with this syringe, but we can see that we can capture the radio frequency signals that it's transmitting, trying to find a pump to contact or sync with. So that's just a bunch of that, just using SDR Sharp and RTL SDR antenna dongle to just capture those signals. And so for kind of a notional demo here, I have a dog that's pretty loud, right? And I have a newborn. And his ears are very sensitive. So when the dog acts up, we have a shock collar that goes around his neck. We don't need to use the shock option because it has vibrate and it has noise, right? And also, I couldn't bring myself to be one of those people that shocks your dogs on a regular basis. Yeah. Yeah, they are monsters. So I'm using this to display front to back how you can transmit, receive, capture, replay. Or we can just go back to the beginning. Okay, so we have the remote that allows you to send the shock or the vibrate or sound command. And when I hit it, you can get these 3 little blips, right? We don't really know what that is. We just know that it's there and we can capture it. And I created a kind of a DIY hack RF because I didn't want to pay for one. I figured I'd just buy the parts to make it myself, which I'll get a little bit more into that in depth a little bit later here. But we can capture those. That's what I was doing here. We're capturing those radio frequency transmissions there. Oh. Okay. There we go. So we're going to replay it using the DIY hack RF, which is what we're doing here, and you can see that those same blips more or less come back to us. So I can just take my DIY hack RF there and just walk around, you know, zapping the dog if I wanted to. So another thing too, it's a little bit scary. That example was just kind of show how you can use open source tools to go ahead and capture these transmissions and replay them. But the thing about the pumps that are scary is that you can set the bolus amount unit here to the highest is 15.50, but I put it to 15.45, and you can basically say, hey, give me 100% of that right now, and capture that signal, and then replay it. Same way that I did with the dog collar. And so then you die if you have diabetes. I grew up with, like everyone in my family besides myself has the sugar diabetes. And so I told this to my uncle, and his face, normally like a rosy red, went to pale. So that shit was scary. And it is true. It is pretty scary. He is my favorite uncle. Wait, did I just say that on here? Oh, okay. So really quickly, just to get into some of the components and what I did here to make this DIY hack RF. It's just so I got a Raspberry Pi attached. There's a screen with a adjustable angling there, power source, and a keyboard, and RTL SDR dongle, and on the backside, you can see here. I had a broken mini USB charging cable, so I just kind of snipped the end of that, placed it on GPIO pin out 4, and that's when you're using RPi-TX or the transmission app for Raspberry Pi. You want to have it on GPIO pin 4 because that's the output, right? So it allows you to transmit signals like we saw in the video, and yeah, Raspberry Pi 3 is plugged into the back here. It's got the pins exposed. That's just the receiver for the keyboard. Yeah, so if you wanted to kind of branch out and abstract from there, you can purchase the How to Be an Asshole 3000 kit. This is I just bought a cheapo drone on Amazon. I have a Raspberry Pi Zero that I wrote a Python script for that takes any EQ files or radio transmission captures and just loops through them. You can also make it so that it loops through different frequencies as well. So if you do have frequency hopping going on, hell with that. We can take care of that. And that too has a cable that's plugged into the underside of the GPIO pins that are exposed on the bottom. And then, so this is a notional concept. You can physically do this. I just need a smaller power source and a Velcro. See, there's no Velcro there. That's, if I had Velcro, this is the specific place I would put it in this picture. But I don't. Yes, yeah, I can. The Velcro aisle. So, some proposed security solutions for IOMT. I say proposed solutions because the devices that are out there that do things like this, they're vast, and the protocols and the way that they do stuff is all different. So one way is unique signal for every insulin pod pump. This is something that they do with car fob keys. So like with newer cars now, each car has their own, signal when they communicate with the key fob to the car. Adapting that same methodology and mindset to IOMT devices utilizing RF frequencies would be another one. The way to do that, I think, is a good one. So making each pod unique, decreasing the attack capability to a single pod. So that way, if I have the captures that I took, I can't just go around killing diabetic people. I got to capture each individual one. Instead of one signal to rule them all. Rolling codes, also known as hopping codes, transmission frequency from the personal diabetic that little handheld thing. That frequency changes upon each use in session. So you are doing frequency hopping, but frequency hopping coupled with the unification of individual pod code would suss out a lot of these, a lot of the attack surface there, or the attack vectors, I should say. So yeah, transmission frequency changes upon each use, and the code would be stored in the pod themselves, ensuring that unique transmission across all insulin pods. That way you can't just take one PDM and manage different pods, and then have to, the code that makes the communication unique is stored in the individual little white insulin pod pumps themselves. So getting in the mindset of that, I think those are good ways to secure RF. So here's the thing, though, too, is that this is known, right? This is known stuff, and if we go onto GitHub here at OpenAPS OpenOmni, we can see that a lot of people have done some of the research before me, so they've done some of the work before me, meaning that they have these, they have all of these captures done, right? So one that I want to show you, the bolus packets. Here is the signal. I knew that. Yeah, so we can see here that we're confirming our units to this. It's basically somebody decoded the CRC encryption on these radio frequency signals and put all of them out on GitHub. So if you have little free time, you can kind of do an abstract step of stuff that I had done. And there's also a tool out there specifically for the RF transmitting insulin pump pods called RTL Omni. It's basically a Python wrapper for the RTL SDR application on Linux, and it is written to use the CRC decryption of Omnipod transmission signals. So instead of fixing this, apparently the solution is to just allow Bluetooth instead, which I'm not joking. That's what they're doing. So next, automotive, connected cars. So here we have a few different pictures. On the left here, we have what is called, what we in the biz call a buck, which is basically, it's the car network, right? So if you're to strip out all the physical mechanisms and everything in the vehicle, you're left with the CAN bus and ECU network and all the wires and stuff that go into it here. Then, yeah, just a couple of illustrations denoting the increased use of connectivity in vehicles. So the vehicles are pretty interesting, though, right? Because in early on, there was no connectivity to a network, right? That just wasn't there. It's all physical. It's all mechanical functions. And in the 80s, we have the introduction to in-vehicle features. So sensors, electronic fuel injections, digital gauges. And then in 86, the CAN bus, or the CAN protocol is introduced, and the CAN bus is just it's a network that ECUs or engine control units use to communicate. And so that's there, so you can just add ECUs to the network easily. And then today, we have approximately 200 ECUs in some cars. And so also new cars have new internet connections, which is the connected vehicles, right? So cars are becoming more and more data, and the vehicle attack surface is increasing to meet the need of these new features faster than security professionals can take action in most cases, I think. So we're going to get a little bit into the CAN bus network, which I don't expect everyone to remember all this stuff specifically, but the idea is to just illustrate how the buck that I showed you, this is kind of how it works in an architectural sense from a high up level here. And the idea is that we want to prevent somebody using the onboard navigation system to pivot to the brake control of the vehicle, right? Which is possible. Getting into the CAN bus frame itself. The CAN bus frame is, again, this is not trying to get super technical in it, but this will probably this will come up later at some point. So just to have reference of it. So you have the start of the frame, which is denoted by just a single bit. Doesn't matter what that bit is, it's just there. The next we have the identifier part of the CAN frame, and that basically just represents the priority of that CAN message. Then next we have remote transmission requests, and really all that is that denotes if it's a data frame or remote request, which you don't really have to know what that is. It's normally going to be 0 for data frames. And then the yellow section here is the length code. So that basically says, hey, other ECU, here's how big the CAN frame is going to be. And then the red field is data. So that is the thing that is being transmitted. So when we're thinking of networks and stuff and looking at network traffic, normally we think of the TCP packets, where you can see things that are very verbal here. So, I mean, we all know what network traffic looks like for the most part, right? So we have the interface name right here. We've got the MAC address, the vendor, or the guest vendor, IP address communication, payload, all that kind of stuff. But the network, how you look at a network in a CAN bus format is a little bit different. You have your CAN frames look like this when you're sniffing the CAN network. So to get a little bit more into that, a video demo. Oops, I had text here. My bad. So moving from mechanical to digital. If your brakes are mechanical, no cyber attacker can compromise them. You can cut them, whatever. But they're becoming less mechanical because we're introducing drive-by-wire, which is basically relying on sensors from the gas and the brake pedal and the steering column to talk to the ECUs that control those operations in a vehicle, and then take care of that for you. And the reason that a lot of this is happening is that we're making this shift into doing things like park assist and drive assist, preparing for the potentiality of completely autonomous vehicles. I say potentiality because as somebody who works in this space, I know a little bit of the nuances that are hard to navigate around. Though some might say it's an eventuality because they're the ones making the autonomous cars. From a security standpoint, it's a little bit different. So CAN bus security CAN bus, CAN protocol, CAN messages, CAN frames, everything that you see on the CAN network is unencrypted. It's unauthenticated. And if you gain access to a CAN bus with other available modules, you can freely communicate to them. Then we're introducing new points of connectivity. The TPMS, or the tire pressure monitoring sensor. It's basically a sensor inside your tire that uses a radio transmission to talk to an ECU on the CAN network that receives those signals. In-vehicle Wi-Fi and Bluetooth. Some of you guys, the fancy cars out there, have internet and Bluetooth connectivities, and you have telematics units and head units. The telematics unit that talks to the head unit. Then you have key fob, which talks to the body control module, which is the ECU that handles your beep, 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 all that stuff. Then anything plugged into the OBD port. So it could be a diagnostic tool, it could be a progressive, has a really vulnerable OBD2 dongle that you can plug in. Then you have data loggers. There are companies that provide services like vehicle analytics. They say, hey, plug this into your OBD port. We get stuff about your vehicle. That can be used for things like going to the mechanic, or it could be used for trying to lower or increase their insurance rates. But they're creating an additional. They're introducing a vulnerability that was probably not there before with that vehicle by doing that. And so a couple attacks that can happen. TPMS attack. This is basically using an RF capture and replay to trigger a low tire sensor light on your dashboard. An innocuous thing in and of itself, but say you pull over at night, you try and check your tire and your car gets robbed. It's like high-tech carjacking. Key fob relay attack, using radio to extend the range of a key. So like the key fobs that the cars that have a key fob that you just have to be in the vicinity and you can push the brake and turn the car on without having to turn a key. Those require a certain proximity. So if I'm in the middle and I'm using a device to extend that signal from inside your house to the car, I can steal the car, drive it somewhere. The only thing that sucks is that when I turn the car off, I can't really turn it back on again. But I'm pretty sure those stolen cars just get parted out anyways. And then we have the vehicle bomb attack, which is I infect my car purposefully, and then I send it to the dealership, which then uses these diagnostic tools that connect to the cloud and do these awesome diagnostic operations and whatnot. But by having an infected car, that kind of spreads some of that throughout. You don't hear about that too much, but it's a definite possibility. Short range, wireless, so hacking Bluetooth and Wi-Fi the same way that you would on a network. It's the same thing, it's just in a car, it's not in an office building or an organization. And then long range wireless with 4G satellite radio doing, like, these are attack surfaces basically. So here I have a demonstration video in which I had set up a virtual car. So think of the CAN bus network. Think of the buck that I showed you before. That's just digitized, right? So it's on my laptop here. I'm going to play that. And so what we see on the left side, these are the CAN frames coming in as they happen. So you can see right here, the gauge is kind of moving up and down a little bit. Then we have a control unit right here that just lets you accelerate or unlock the doors, do signals, stuff like that. So I'm going to go through and just kind of do a couple of controls, increase the speed to about, I think, 80 miles an hour, do a couple things with the signals here. So we're actually seeing the CAN frames over the CAN network as they happen. And so we're increasing the speed. And then I'm going to let off the gas, let that go down a little bit. then I'll do some other stuff. There we go. Unlocking doors. And so I'm just kind of continuing to unlock doors and play with the controls there. Not a lot of them. Some of them do have like units and stuff installed, but as far as motorcycle CAN networks are concerned, I'm actually unsure. I can say it's similar, but I can't speak for it. All right, so now what I'm going to do is I'm going to end up sniffing the network in the same way, but I'll be doing an actual, like, capturing those CAN frames that come through. So all the things, man, I type slow. I'm just going to fast forward a bit here because there is some stuff going on. All right, so we're going to play the capture that we just did. While using the CAN sniffer there. The best way to do this example is to turn off that controller. That way you're not keeping things going on the UCU network there. But yeah, so with doing a replay, the replay is playing now, so it takes a second, and you'll see the car automatically speeds up. And this is scary. So like imagine you're pulling up to an intersection and your acceleration ECU cuts off and all of a sudden you're slowing down, but then you're accelerating. That's kind of scary there. And to solidify some of what I'm talking about here, I will be playing, just got a few minutes of this here. A few years ago, a couple of researchers figured out how to hack a car remotely. So pretty much this guy's going to be on the highway, and these two guys are going to be controlling his Jeep from their home.
In its dashboard. Now they're sending the same sort of attacks remotely, and I have no idea what they might do.
He's going as fast as I've seen him, so.
So first we're going to turn the fan on him.
Yeah, let's turn the fan on, see if he even notices.
Alright, something just turned on, all the fans and AC and stuff. I didn't do that.
The trick started small.
Oh my god. There's a picture of Charlie and Chris in tracksuits that just appeared on the dashboard.
But as I drove down the interstate, things started getting unpleasant and very loud.
For time's sake, I'm gonna expedite some of this here, make it.
Right now.
There we go.
Do it. Kill the engine.
So we're killing the engine right now.
On the highway.
Actually, accelerate.
I stomped on the gas, but the Jeep slowed to a crawl.
It says 40 miles an hour, but I'm not going that fast.
I turned on my hazard lights, but I was still stuck in the right lane with no shoulder to escape on.
You gotta turn.
Yeah. So pretty much you had to turn the car off and on again. Typical IT reaction, right? So let me get back here. I'm kind of speeding up some of that here because I eating up a little bit of time. Okay. So back to there. Okay, so proposed solutions for automotive security. Secure gateway. Secure gateway is basically just segmenting the CAN bus network, basically the same way that you would an IT network in sense. Considering the OBD port untrusted, so anything that can stick into your car from the outside should always be untrusted, and it would require an unlock signal from the car itself to be allowed through. So diagnostic tools do have internet connections. They can get unlocks from OEMs, and they can pass to the secure gateway. Basically, network segmentation. That's all I'm trying to say. Network segmentation. So you have a telematics unit. You have an OBD port can go in, and then if you're talking to the head unit here, you can see each of the ECU networks for powertrain transmission is split off into two. Body domain, safety chassis domain, that's all split off from the non-secure side of the CAN network. It might look a little bit different, but if you work in networks, you'll understand the process of network segmentation here. Vehicle intrusion detection system. There are a few companies that are doing this already. Karamba, an Israel-based company, is one of those. What it really looks like is the putting analysis on the gateway module, doing anomaly detection. ECUs have standard communications, so if there's new stuff going on in the car, you can, do that anomaly detection in your intrusion detection system. Kind of going from there, it's like, now you know something weird's going on with the customer's car. What's the next steps from there? We don't really know. Honestly, we don't know because there's a lot of liability issues to hammer out. So while the technology is there-ish, it's not integrated, so it's still a concept. But the idea being we can put CM in cars. That's really it. And so here's what that might look like from kind of a optimistic point of view here, having an actual security operations center that's taking in info from all different data sources and working that in like a security operations center would. Okay, getting into industrial control systems. That is, we covered that a little bit before. It's a term that covers the control systems and everything that goes into it. And we get a little bit into SCADA as well, which is basically like the management network stuff for it. I'm going to be blowing through some of these here, just again, time-wise. Where are they? They're everywhere. Streetlights, water treatment facilities, solar farms, oil production lines. Those of you who've been in some of my talks, I bring up the Klondike factory example. I will give the same disclaimer that I do if you've ever been to a Klondike factory and you want to correct some of the things I'm talking about. I don't give a shit. I don't care. This is just to denote a process in how controllers control things. So let's say the Klondike factory, you have the machines that make the batter for the ice cream. You have a refrigeration unit that refrigerates those, and then you have the things that go into squares, right? The ones that are in squares, they are packaged and shipped off. So you have PLCs, or programmable logic controllers, which are tiny computers that manage the processes of each thing. These controllers can hook up to HMIs, which is basically just the point-click interfaces that might sit in a cabinet somewhere. And the way this works is that in the process, PLC one that manages the batter stuff, that will say, hey, we're good, and send a message over to the next PLC, which then says, hey, we're good, refrigerate. Once it's refrigerated, it goes to the next PLC saying, hey, put the shit into squares. Once the shit's in squares, you then move it over to packaging and shipping out, right? That's an easy way of just getting that process in your head. And if in this manner, if one PLC fails, the rest will not work because it's relying on signals saying that the process is done. PLC is a small ruggedized computer. Normally, you put these on racks. So you can have a PLC unit right here. You can be adding additional CPU or an RTU, remote terminal unit or something, and then that rack goes into a cabinet. And you can also have a long-distance connection to the device itself, like that, so it controls something from afar, or right next to it. Programming languages, there's a bunch of programming languages right here. Ladder diagrams, sequential function charts. Basically, a lot of these are ladder logic or abstracts of ladder logic. Multiple protocols used. So PLC manufacturers, a lot of them will kind of make their own secret sauce, right? They'll say, hey, this is my communication protocol. And there's no real standardization of that. There are some. There's the IEC, but these are a few different protocols that are used for PLCs to communicate. And function codes, holding register addresses, programming coils. Programming coils basically consist of ladder logic drawings with a binary output. Holding register addresses are 16-bit words that are numbers. It's like counter presets, accumulated values, math results, or whatever. SCADA, secured supervisory control and data acquisition. This is just saying this is the top of the hierarchy. This is you can control and delegate tasks to different PLCs from there and do all the analysis and data gathering from there. I'm not going to read all that. We'll be here even more past lunch. This was how like a SCADA network from a very high, simple level can look. You can also have a PLC you can have a controller that controls the controllers. You can have the SCADA device, and you can have a controller that controls the controller that controls the controllers. Or you can have a SCADA device with a controller that controls the controller that controls the controller, right? You get the message, okay. That's just being a bit silly. But again, just trying to drive that point home here. So what we get into with industrial control systems is IT-OT convergence. I talked about a little bit this before. Basically taking the operational technology network or the IIoT, industrial IoT network, or the IC, whatever nomenclature you want to use, basically saying, take this and I want to talk to the IT cloud analytics system doing everything remotely, right? So that's when we get into bridging the air gap. That's the process of making those communications secure. So the concept is that a physical gap can stop attackers, but the idea is if you want to do this convergence, you can't really do that. And so the goal of it is to take the operational technology network and to marry it with the IT network to work with each other. And then the expectation is that things will work in harmony, like this oddly is. But then what really happens is a large influx of companies and entities rush to meet industrial relevance, new features of communications, management, analysis tools, all the flashy stuff, right? And so you have organizations that rush to bridge this gap, and they drop the ball. The ball is security. And then there's bomber, and there's fire. And then there is this guy falling flat on his face. And just to get into a little bit of some scary stats, these are things that I've seen within the past few months. These are just different types of PLCs or SCADA devices that are open on the internet now, or they're visible on the internet at least. So you can see Modbus, Tritium, and Siemens are three of the bigger offenders here. And again, putting your stuff on the internet is just asking for things to hit it. And the way that these communications work is that if you have a PLC or a SCADA device on the internet receiving signals it's not expecting to, things will break. Okay, so really quick, I've got a quick live demo that I wanted to do. They're going to miss the demo. Their loss. Yeah, so I'm going to go ahead and Yeah, I am fully aware that it's gone a little bit over, but I'm lucky to have the lunchtime spot, so thank you. So I'm going to get into a tool that I actually released open source at KakalakiCon this year called RapidFire. And RapidFire is a tool, well, when I did my first pen test ever, there was a lot of iterative functions and things that I had to loop through. That the tools that I was using at the time were only accounting for single interactions, and so iterating manually would be a pain in the ass. So I created a tool that would rapidly query the things I needed to, hence rapid fire, because it would rapidly fire off the queries. There we go. So So I've got a virtual PLC running, right? And so we're going to enter the Modbus module of RapidFire. And we have a few different options here, but for expediency's sake, I will just go into the Modbus testing framework, which is, I'm doing that thing again. Why didn't nobody say anything? Thought I was sharing it. Here, I'm just going to mirror displays. Make it a little bit easier for me. Yeah, so here we have RapidFire. We're inside. Yeah, let me get back out real quick. This is what it looks like when you open it. We're going to go into the Modbus menu here. We're going to go into number 5, which is this mod framework. Oops. And we're going to go ahead and get the functions of a target PLC. Let me just set these real quick to our target PLC, which is home. We're going to set the UID to 1 because I know that UID is 1. And we're going to exploit it. And we're going to identify the different function codes that are on the virtual PLC. The function codes basically say, hey, this is what the PLC can do, right? And once we have a few that we can see here, we can see that we can function code 3 and function code 16, that's active, meaning I can read a register and I can write to it, which is a no-no. And the same thing with coils, so code 1 and code 15 are active. So what I can do really quick is I'm going to open up a new tab here, and we're going to take a look at what these look like. And what we'll do here is just set up a watch for the device's current. That's the coils. I don't want that. Okay, we'll stick with the coils then, just for expediency's sake. All right, so we can see this is just binary output. This is the logic of the controller itself. And we go back into the Modbus. We can go into coil injection, target IP address, put it in there. Please enter start address. That'll be 1. And address will be 19. And what we want to put in it, that's fine. We can see we just rewrote all the coils, all the coil values, right? So that's a no-go, because if you can talk to a controller on the internet, you can query certain things about it. You can see that the function codes are open. You can do this and break whatever processes those things control. So going back to the presentation. Okay, so demo time for that is over. Okay, so we're going to get into a little bit about the network. We saw a little bit of this before, but we're just adding in this little cloud analytics symbol here. So we're going to do a little bit of a high-level, lightweight threat modeling, just very notional, very high level. What are we building? Secure architecture, conducive for IT/OT convergence security. Again, it's going to be that same diagram here. What can go wrong? A lot of things. Incoming communications from any kind can compromise the system. PLCs have very rigid communications they're expecting. So if anything kind of is off kilter, things will break. So here we have a trust barrier saying anything that goes out is fine, but anything coming in from over this trust barrier is not good. So what are we going to do about it? We want to protect the network from unsolicited incoming traffic. And so by doing that, we don't want to do this. We don't want to just stick it right on the internet like that. So we want to test it. So when we have the network up, this is a unidirectional gateway, or just, I'm going to get into that a little bit. But we're basically just having somebody test if they can try and communicate to the SCADA device or the PLC from the outside, much like I kind of just did in the demo, right? I shouldn't be able to talk to anything on a PLC. It shouldn't be on any internet in that way. Yep, that's redundant. So there are ways to secure this that I came up with here, or that I'm going to talk about. Combining, like basically just an advanced network architecture, so combining layers and obfuscation, stuff like that. So we can have a couple examples here of a SCADA network that's segmented, basically separating the IT and OT traffic. Then we have another one where we have relay servers set up to send data out to the cloud if you really want to do that. This segmented network handles just it's a relay server handling incoming information from here, and it's over a one-way VPN connection, some kind of network trunk going on here. Then getting more to the network trunk side, we're looking at basically saying, if you don't know how network trunking works, this is kind of just a quick in-your-face, here's how it would look. Basically saying everything from this the OT segmented network would talk to the segmented network for the relay servers, coming out, utilizing some kind of reverse proxy technology that if somebody were to try and get back to it, you might be able to reroute that to a honeypot, right? And you can send all this stuff to a security monitoring server, your IDS collector here. And you'd also have a tapper span port to do the same thing. And that's something I've set up a lot of times, and it's really a really valuable thing. So employing hardware at the network level, restricting traffic. This is talking about the unidirectional gateway. Unidirectional gateway is basically a network device that makes it so that traffic can only go out using a one-way data diode. And they exist both as hardware and software. Waterfall Security makes the hardware for it, and then there's a tool called Hair Gap, which is a one-way network transmission. It works. I just don't like it as much. So this is what a network would look like that uses unidirectional gateway. You'd have the diode saying stuff can go out, but it can't go back in. then we had this example again. The last way, I promise we're getting close to the end. I've only got a couple more slides left. The last way is using HIP. HIP is a host identity protocol. It's a host identification technology for use on IP networks. And we're basically adding a whole new namespace to internet conversations, right? So the host identity namespace is based on a PKI, or public key infrastructure. The advantages of this is IP address is only used for location of a thing on the network, so that's the address. Native security and verifiable cryptographic identities are bound to any IP-enabled devices. Mutual authentication, authorization before transport, and trust secured communications. So you know that every time that you're talking to something on the HIP network, that is that device. It's not being spoofed. It works over NAT, so it's all NATable. You don't have to, and when you're NATing, you don't have to open up all the ports that you would need to. Think of like if you're doing, kind of like if you're doing a VPN, but the difference is the peering is from peer to peer, you don't have to route it through the VPN. It still gets routed, it can be routed through a relay, which I'll get into in a second, but disadvantages are that it's really hard to set up, meticulous setup involved. And so here we're just going to kind of get into little visuals here. So say if you have a regular IP network where you have the SCADA device right here, Acme Corp, whatever IP here, you're talking to a cloud service application that's for, SCADA analytics and stuff. The HIP network would be an overlay. So instead of an IP, you have what's called a local scope identifier, which looks like an IP. It's got 4 octets, but it's all weird and fucked up looking. So when you're talking from here to here, there's no possibility of being spoofed because before that communication even happens, a PKI-based trust happens before that, right? And we can also look at this in the form of a relay. So basically, let's say that your SCADA network has, let's say you have 2 factories and you have 2 SCADA devices that you want to send to the cloud. You can do this way, or you can do this way through a HIP relay. Anything that's connected to the relay, you can do what's called wide area segmentation, microsegmentation, basically saying, at a whim or the drop of a hat, this can talk to this can't talk to this, everything is kicked off the network, oh shit, mistake, bring it all back, right? You can do that very quickly. And so I'm going to introduce you to a tool called Defiant. The Defiant that we all know and love is the USS Defiant that Captain Benjamin Sisko commands. It's the only ship in Starfleet to have cloaking device, which the Romulans provided during the middle of the Dominion War. And that brought the Romulans into the fold there. Anyways, yeah, so that's really important stuff, but I got to skip that. Here is a demonstration of a tool that I made that makes implementing HIP easy. And you have a relay, and the relay, everything is connected to it. But from the relay, you can actually decide what can and can't talk to one another. And I call it Defiant because it's a cloaked network. And the USS Defiant was a cloaked starship. So really, I'm just going to fast forward a little bit to the end here. You can get the, if you do server info, you get the local scope identifier, the information that you need to add new networks and copy and paste it. But really what we can do is identify the agents connected. So we have Taco Bell, we have HIP test, and we have test. And if I want to, I'm going to run the connection manager. The connection manager allows me to, I can pick one of these, I can see if it's active, and then what I'll do, I can tell the tool to say which agent at an endpoint do I want to control. And I do that. And it tells me what connections those have. We have Taco Bell, and some bullshit test. So we're going to get rid of, we're going to remove some bullshit test. And I mean, yeah, that's pretty safe. It's not pretty or cool, but it does work. That's the point. So being able to do wide area microsegmentation is really valuable. So today, I know a lot of people left because it is lunchtime. I'm gonna release it right now. That's not working here. No. Anywho's, yeah, I was gonna open source it, but I'm having issues with. Yeah, I'll try one more time before I stop. Oh, yeah. I'm an idiot. One last time. If that doesn't work, then that's... Oh, there we go. Yeah. So I got it. Got that, and then I need to... All right, so I just pushed the agent. That's open source now. Now I'm going to do the same thing with the relay. Frowny face. Okay, so that's that. Okay, and if we go, if I refresh this, it should be full of stuff. Yeah, so, yeah, that tool that I showed you to do the microsegmentation is now on the GitLab, so anybody can use it if they want to. And, yeah, GitLab links are here if anybody wants some of these. The agent and relay, unfortunately, I only have it working on Zorin OS. However, I am working on a containerized solution for rapid deployment. Then rapid fire is down here as well. Okay, and then to do a recap, Cyberphysical technology, digital action with physical reaction. It's everywhere. It's necessary to further our industrial advances. There's a lot of it is insecure. IOMT, convenient but not really secure. Lots of open source intel on how to hack IoT devices, especially those using RF transmission communication methods. Rolling signals and codes are best way to perceived to secure, from my point of view at least. Following what cars are doing, at least. And then automotive feature-driven development increases the attack surface of the vehicle. Industrial control system, automation systems are open to the internet, making things easier. It's a big no-no. They can be secured through advanced networking schema, unidirectional gateways, or host identity protocol, like I showed before. I got to give credit where credit is due. So Zombie Craig, who is an automotive hacking expert, he's the author of the Car Hacker's Handbook, Guide for the Penetration Tester. He created the tools that basically let me do the virtual car with a virtual CAN there. And that's his GitHub. He's got a few good things on there I like. Next, Dr. Bryson Payne, Funding Director, Center for Cyber Operations Education. A lot of the research that he did kind of simplified how to do your own demos, and I really like that, so giving him a shout out here. And then the Block Harbor CEO, Brandon Barry, he is probably the most known, foremost automotive cybersecurity expert out of Michigan. He's the one that introduced me to it, me to automotive and other areas of cyberphysical. And one of his accomplishments is at this past DEF CON, his team won the car hacking village. So hacking a Tesla and like other smart grid type stuff, his team won that. Additional shout outs for equipment, subject matter knowledge, or just inspiration. Alex, Mohammed, Spacer, and Kyle. And my contact info is all that. Basically, every handle is Taco the Boss. That's really it. And if anybody wants to email me or do any collab or just say hello, you can reach me on any of those. Shit. Yeah. Yeah, that's it. Thank you for sitting through that. Is there any questions? Any inquiries? Yes. Yeah, I can do that. Any other questions? No questions on HIP or rapid fire or the history of UTP? No. All right. Cool. Awesome. Yeah. Thank you. Thank you. Sticking around for lunch, Sam, or no? Okay. Yeah? Well, what year are they? Yeah, so those, the vulnerabilities that I showed in the video, I couldn't get into the details, but pretty much there was a tool that allowed their network to be seen on the internet. So you can see Jeeps in real time based on their location. And you can interact with this, and there's Python libraries out there that you can just import to simple scripts and talk to like whatever IP address that port. I think it's like 6607 or something like that. And there's still some out there. I mean, Shodan. I was gonna get into Shodan today, but I didn't. I finally looked down. I'm like, I'm in 40 minutes. Shit, I couldn't. Yeah. Somebody might have used the range extender. I mean, yeah, that's really what this is, just trying to make you aware of the expanding attack surface that cyberphysical technology is. It's compounding, and it's coming out fast. Yes. Mm-hmm. Yeah. The one on the back is there's like Wi-Fi tea kettles out now too that you can break into and get the Wi-Fi passwords. It's like typical. Yeah, that's.
Yeah, the toilet.
Yeah, so some of the graphics that I showed with the